When we measure velocity, we need to know what we're measuring that velocity with respect to. Typically, we would measure the velocity with respect to ourselves. So if I'm sitting in a train car that's traveling across the country and someone throws something across the train car, I would measure the velocity of that projectile with respect to the train car, with respect to me, because I'm moving with the train car. Someone standing on the ground would see the train car going by and then this projectile going by and would measure the projectile's velocity with respect to them, with respect to the ground. And when we're moving, how do we measure our speed? Usually with respect to what we're moving through. So a car travels across the ground, it would measure its velocity with respect to the ground. A boat moves through water, it would measure its velocity with respect to the water. And an airplane would measure its velocity with respect to the air that it's moving through. A quick note about nomenclature. I'm going to use subscripts to indicate how the velocity is being measured and who with respect to what. So when I write it like this with these subscripts AB, it means I'm measuring the velocity of A with respect to B. So if I was measuring the velocity of a car with respect to the ground, I would write it like this. V sub AB is the velocity of A with respect to B. V sub CG, the velocity of the car with respect to ground. One more thing I want to mention about this. What happens if we switch places? Maybe this little example will help. If I'm walking this way across the classroom at 1 meter per second, you see the velocity of Frank with respect to you is 1 meter per second to the right. But I don't think I'm moving. As I move this way across the classroom, I think you're moving to the left at 1 meter per second. So you would say the velocity of Frank with respect to you is 1 meter per second. I would say the velocity of you with respect to Frank is 1 meter per second to the left. So if we flip the subscripts, we rotate the vector 180 degrees. The velocity of A with respect to B is opposite the direction of the velocity of B with respect to A. This is our velocity addition equation. It tells us what order we add the vectors. A key to using this equation is that the first subscript has to be the same. Velocity of A with respect to B is the velocity of A with respect to C plus the velocity of C with respect to B. The last subscript has to be the same. And the two in the middle have to match. I think the best thing to do is to a quick example so you see how this is used. We'll start out with a one-dimensional motion problem. Then we'll get into more interesting, complex velocity addition problems. In our first one-dimensional velocity addition problem, we have a train moving to the right. The velocity of the train, measured with respect to the ground, is 24 meters per second to the right. There's a person running to the left across this train car. The velocity of the person is measured with respect to the train car that they're running on, and their velocity is 8 meters per second to the left. That's a fast person. Let's use our equation to figure out what the velocity of the person is with respect to the ground. Someone on the ground would see the person moving, and how fast would they see the person moving? Well, let's think about it for a second before we do the problem. If the person on the train was just standing still, someone on the ground would see them moving at 24 meters per second to the right. But they're moving to the left. So we're going to see them moving a little slower than 24 meters per second. We're going to see them moving 16 meters per second to the right. But let's do it with the equation and we'll see what we get. So this equation tells us the velocity of the person with respect to the ground is going to be the velocity of the person with respect to the train plus the velocity of the train with respect to the ground. Does this match our equation format? The first subscript is the same, the last subscript is the same, and the two in the middle are the same. So we're good. We have to add the vectors like this. And we know how to do graphical vector addition. I'm going to use blue for my first vector, the person's speed with respect to the train. And that vector would look like this. Then I come out to the tip of that vector and I add my next vector, which is the velocity of the train with respect to the ground. And that's to the right, 24. And so the resultant is this red vector, starting at the starting point, going out to the tip of the last vector. That's the velocity of the person with respect to the ground. And I get out my ruler and my protractor. I see it points to the right, and I see it has a magnitude of 16 meters per second. We didn't really need to do graphical vector addition to figure this one out. But let's keep working, and you'll see it is handy when the problems get a little more complex. This time our person is running to the right, and the train is going to the left. Same process. I'll use blue for the velocity of the person with respect to the train. This is a vector addition problem. I'll use gray for the train's velocity with respect to the ground. And I get out my red pen for the last vector, the sum of those two. And that's going to be the velocity of the person with respect to the ground. And I add those up, measure the length. I get 20 meters per second, and it points to the left. In our last example, we've got the train and the person both moving to the right. Again, think about what it's going to look like to someone on the ground. That person on the train is going to be really moving, right? If they were just standing still, they'd be moving at 20 meters per second to the right, but they are moving to the right with respect to the train. So we're going to end up adding these. We're going to get a 32 meter per second velocity to the right as measured by a person on the ground. But let's see what we get. We'll use blue for our first vector, do the graphical vector addition. Use gray for the other vector, train with respect to the ground. Red for our resultant vector. And what is the result when we add those two together? Person's velocity with respect to the ground is going to be 32 meters per second, pointing in the direction of that red vector. Now we could do all those in our head. Let's make it a little more interesting by doing a two-dimensional problem. We'll keep it simple in this first problem by choosing the two velocities to be orthogonal to each other. Then in subsequent examples, we'll make it a little more general. So in this case, we have a boat crossing a river. Now we're going to make our river special. Of course, in a real river, the velocity of the water changes as you move across the river. It's slowest at the banks of the river, and it's fastest in the center of the river. We're going to make our velocity the same everywhere across the river. And we're going to call that the velocity of the water with respect to the ground. And it's going to equal 2 meters per second. So the magnitude is 2 meters per second. The direction is to the right, and the water has the same speed everywhere. Our boat is going to leave point A, and it's going to point straight across the river, always pointing straight across the river. And it moves through the water with a speed of 5 meters per second. And as we said, it's always going to be pointed in that direction. So is our boat going to get to point B? Of course not, because the water's pushing on it. And as the boat tries to get across the river, the water's pushing on it and pushing on it. And where's the boat going to end up? Somewhere over here. Let's call that point C. So if you were in a helicopter looking down, your boat would be traveling across the river like this, and it would hit the shore on the other side at point C. So we'll take a look at our formula here. Our formula tells us that the velocity of the boat with respect to the ground, that's what we're trying to find, the velocity of the boat as seen by someone on the ground, is going to be the velocity of the boat with respect to the water plus the velocity of the water with respect to the ground. So first I'll get my blue pen out and I'll draw a vector for the velocity of the boat with respect to the water. That has a length of 5. Then I'll get my gray pen out and I'll draw the velocity of the water with respect to the ground. That has a length of 2. And then my red pen is going to be the resultant, the sum of those two vectors, which is that one. And that's exactly what we said it was going to look like. We said if you were in a helicopter, it would look like the boat was going straight from point A to point C, and that's what we got when we did our vector addition problem. So we need to know the magnitude of that vector, and we need to know some angle, some orientation, some direction. So I'll measure the angle theta there. I just draw a picture and measure it so I know exactly what it is. VBG, magnitude. Now we picked vectors that were orthogonal to each other, so we know we have a right triangle here. This is going to be the magnitude of this vector squared, and the magnitude of this vector is 5, plus the magnitude of the other side squared, that's 2, square root. So that's going to be the magnitude of our velocity of the boat with respect to the ground, and of course the units are going to be meters per second. And theta is going to be the inverse tangent of 2 over 5. In the next video, we'll choose two vectors that aren't perpendicular to each other. We'll have the water in the same direction, but instead of our boat going perpendicular to the water, the boat will be moving at an angle with respect to the water that's not 90 degrees.